in this lecture, we are going to summarize the one-stage op-amp and finally build its data sheet with all the parameters that we have calculated for it so far. So, if you were to take the one-stage op-amp shown here and you had to represent it by a block diagram, it turns out it is best represented by a block called an operational transconductance amplifier, or an OTA. Why do I say this? So if you take a transconductance amplifier, it turns out that its properties are that if you were to apply a delta V at its input, you would get a current delta I which is proportional to delta V, with the proportionality constant being some Gm. And more importantly, the OTA has a very specific property that its input impedance is infinite, and because it acts like an ideal current source at the output, Z out is also infinity. It turns out that for our op-amp, for the one-stage op-amp that we have built, R out is RDS2 parallel RDS4, which is quite large. So remember that one of the properties we desired originally from the op-amp was that the output impedance should be very small. Normally, most CMOS op-amps do not necessarily have this property. The reason why this property is not needed is because many op-amps end up driving capacitive loads, where the low output resistance does not matter too much. Now, let us look at the non-idealities of this op-amp, of this OTA. Now, it turns out that Zn is equal to infinity is valid at low frequencies because the input of the op-amp that we have built is capacitive. Z out is not infinity, but it is quite large, relatively large compared to the other impedances in the circuit. Now, if you were to draw the non-idealities, you could represent the op-amp in the following manner. So, this is the positive input and this is the negative input, and it turns out that the transconductance of the op-amp is small gm1, in other words the gm of m1 and m2, and if it were driving a capacitive load at the output, it would also have its own output resistance that can be represented by R out. So this is the representation of the one-stage op-amp with idealized components. So you have a transconductor representing the GM of the op-amp, and you have a output resistance R out, and you have the load capacitance at the output node, which is CL. Now, if you were to draw the gain of this op-amp as a function of frequency when driving this capacitive load, it would look like this. So I am going to draw only the magnitude plot. I encourage you to draw the phase plot as a homework exercise. So if I were to plot the magnitude of the gain of the op-amp, so at very low frequencies, the gain of the op-amp is clearly Gm times R out, which of course is Gm1 into RDS2 parallel RDS4, because R out is RDS2 parallel RDS4 and Gm is equal to Gm1. Now it turns out that because you have a resistance R out and a capacitance CL, this particular op amp is going to have a pole, and the pole frequency, I'll call that omega P1, is going to occur at 1 over R out times CL. Since R out is very large, this would be the dominant pole of the system and would be quite small. Once you hit this pole frequency, the gain starts to fall at the rate of minus 20 dB per decade. Please note that everything is being plotted in dB. Now, the unity gain frequency of the op amp, that I'll denote by omega U, is clearly related to the DC gain and omega P1. So this is nothing but GM1 times R out into 1 over R out CL. This is clearly GM1 over CL. So please note that if you have a transconductor driving an RC kind of load, the unity gain frequency of the system is the transconductance over the capacitance. So it is GM1 over CL. Now it turns out that this op amp has a couple of more non-idealities. So it turns out that, as we have studied before, there is some parasitic capacitance here which we'll call Cx. It turns out that this particular op amp also has a second pole at minus. So since we are plotting only for positive frequencies, I'll just show the positive value. It happens to be a left half plane pole, but I will only show the magnitude. It has a second pole at GM3 over Cx. And we have calculated this in a previous lecture, and it also happens to have a 0 at 2 GM3 over Cx. So if you were to show this with blue color, the op amp should have been designed such that omega P2 occurs after omega U, so that it's till it hits a gain of 1, it looks like a single pole system, so that it starts going down faster until it hits omega Z, and then it starts going down at 20 dB per decade again. So this would be the magnitude plot of the system. I encourage you to draw the phase plot of the system as a homework exercise. Now we are now in a position to start writing down the data sheet of the op amp, which is going to consist of around 8 parameters. So this is the data sheet of the one stage op amp. This will just summarize the various parameters that we have studied so far about the one stage op amp. So the first important parameter of the op amp is going to be its DC gain. When I say DC gain, I do not necessarily mean DC signals applied, I mean low frequency gain. So the DC or low frequency gain of the op amp is nothing but GM1 into RDS2 parallel RDS4. Now please note that this gain is quite large, and you would expect that this would be of the order of the intrinsic gain of the op amp, intrinsic gain of a transistor. Therefore, you would expect to achieve gains of the order of 100 or 200. So you should, with a single stage op-amp, you should expect to get a gain of about 100 or so. Now, if you were to, if you wanted more gain, it turns out you will have to go for a different kind of op-amp that we'll discuss in future lectures. Now, the second important characteristic of the op-amp is going to be the unity gain frequency of the op-amp, or omega u, and as we have just studied, omega u is GM1 over CL, and as you can see, the unity gain frequency of the op-amp depends only on its transconductance and the load capacitance that it is meant to drive. If you need a larger unity gain frequency for a fixed load capacitance, you have to increase the transconductance of the op-amp. The third parameter of interest for us is again related to the frequency response. So we are now interested in the non-dominant poles and zeros. And as we have seen, you have one non-dominant pole and one non-dominant zero due to the non-idealities of the op-amp, of the single stage op-amp. So you have omega P2, which is minus GM3 over Cx, and you have a 0 which is minus 2 GM3 over Cx. You happen to have one non-dominant pole and one non-dominant zero. The fourth parameter of interest is going to be the input referred offset of the op-amp. Which we'll represent as sigma squared OS in. And as we have seen, this consists of two portions. The first portion is the offset voltage of the input differential pair M1 and M2 that appears directly at the input, and a second portion which is scaled by GM3 over GM1 squared. The second term is the VT mismatch of transistors M3 and M4. So this is the expression for the input referred offset voltage. As we have seen before, if you were to minimize the offset contribution of M3 and M4, you have to decrease GM3 relative to GM1. The fifth term that we are interested in is the input referred noise. In this case, because the op-amp has an infinite input resistance, we only have an input referred noise voltage, and En squared by delta F is nothing but 16 kT by 3 GM1 into 1 plus GM3 by GM1. Again, as we have seen before, to minimize the input referred noise voltage, in other words, to build a low noise op-amp, you will need to maximize GM1 as well as minimize GM3 relative to GM1. The next important parameter is the slew rate of the op-amp. For this particular op-amp, the positive slew rate is equal to the negative slew rate, which is equal to 2 I naught over CL, where 2 I naught is the total bias current of the op-amp. Another important parameter, metric of the one stage op-amp, of any op-amp, is the input common mode range. And as we have studied, for this op-amp, we can write down the input common mode range as follows. So VGS1 is the gate source voltage of the input transistors. If the common mode voltage keeps going down, the current source goes into the triode region, and at the edge of the triode region, if the current source were to have a VDSAT, which is VDSAT5, the minimum input common mode permissible is VGS1 plus VDSAT5. And the maximum permissible voltage happens, as we have seen, when the input transistor goes into triode, and that happens at VDD minus VSG3 plus VT1. Finally, the last parameter of interest for us is the output common mode range. It turns out that for this op-amp, the output common mode range is also related to the input common mode range. As you keep reducing the output common mode, the minimum voltage that it can achieve is related to the input common mode as VCM in minus VT1. And the maximum common mode voltage is nothing but VDD minus VSD SAT 3. So this completes the data sheet of the one stage op-amp. As you can see, there are 8 important parameters that we have listed out and summarized for the op-amp.